Dual. Dual, that means just we find out the duality of any original problem. Any linear programming problem is given, we calculate the duality of that programming. So just we take the transpose of the matrix and changes the sign if the original problem given in the form of the less than equal to. So we may write the dual of that problem, we take the sign as greater than equal to. If the problem is maximization, we write the minimization. So this is the duality. This is the important concept of linear programming problem. Important concept of linear programming problem. So the fact is that every linear programming problem can be, can say that associated with another linear programming problem. Associated with another linear programming problem. The original problem is called primal. Original problem is called a primal, while the other is one while the other one is called dual. So this is also very useful. That means if the optimal solution of one is known, then the optimal solution of other will be available or can be determined easily. Yeah, we write as will be available. So the important fact Because of the situation, the important fact is sometime may arise where the dual is easier to solve than the primal. Sometimes you see that we cannot solve the problem directly. Directly means directly a primal form. So we take just the dual of the problem, and after taking dual of the problem reduced in the simple linear programming problem, and we can solve it easily. So the concept of duality duality in linear programming problem. Concept of duality in linear programming problem. So we consider a problem related to diet problem. Regular we take the diet. So the amounts of two vitamins V1 and V2 per unit present in two different foods. Different foods. Name of the food is F1 and F2 respectively. Vitamin V1 and V2. Food F1 and F2. The quantity is 5 and 7. Second one is 6 and 11. And here is the cost per unit. Cost per unit. So the cost per unit is first is 10 rupees, second is 15. 15 rupees. And minimum daily requirement, minimum daily requirement is 80 and next one is 100. 80 and 100. So the problem is to determine the minimum quantity of two foods. The problem is to determine the minimum quantities of two foods. F1 and F2. F1 and F2. So that the requirement, so that the minimum daily requirement minimum daily requirement of two vitamins is met. Same time, the cost of purchasing these quantities of F1 and F2 is minimum. So this is the problem given in the form of theoretical. So first we formulate the problem. The formulation we already studied in LPP, or we also discuss in NLPP. So just first we formulate the problem, then after formulating the problem, we write the dual of the problem. So for formulation of the problem, that means here we take first we formulate the problem. Let x1 and x2 be the number of units of food be the number of units of food f1 and f2 respectively. To be purchased the problem is to find the values of is to find the values of x1 and x2. x1 and x2. So the objective function of this problem, that means minimum quantities, determine the minimum quantities of food and daily minimum requirement. So objective function in this form, minimum of minimize the objective function z, which equal to the cost of each item 10 and 15. So 10x1 and 15x2. 10x1 plus 15x2. And subject to constraints we write directly, that means food of 5x1 plus 7x2, minimum daily requirement which is 80. Minimum, this is minimum requirement, so we take the sign 5x1 plus 7x2, or this is the minimum requirement, so we take it's greater than that, means minimum requirement is 80. So we take the greater than sign. That means this LHS part may be greater than the RHS. Because we want that the minimum requirement is 80. We cannot adjust with less than 80. So first subject to constraint in this form. And second constraint we make as 6x1 and 11x2. 6x1 plus 11x2 and greater than equal to 100. Greater than equal to 100. And both the decision variables we assume x1 and x2 are greater than 0. So this is the formulation of LPP. And suppose we write the dual of this problem. So when we write the dual of this problem, so that means we choose the same variable as x1 x2. In place of x1 x2 we write the variable as y1 y2, or any other variable you can choose. So we have some rule, that means when we write the dual of any problem, So here we formulate this problem, then after formulating that problem is known as the primal form, original problem. Here we use the variable x and write the dual of this problem. So for writing the dual of this problem, so we remember some points. First point is that write as to write the dual of the problem. Remember the given problem, yeah, the primal form has objective function in minimization, then its dual, then its dual having objective function maximization. The problem having less than equal to sign, then its dual having greater than equal to sign, having greater than equal to sign, we replace the variable x1, x2, xn, we write journal form with another variable, suppose y1, y2 and yn, or we can write as omega 1, omega 2, omega n. We make the transpose of the matrix. The last one, we write the inequality. Inequality means less than equal to, we write with the objective function. We write objective function of dual as yi and bi. That means transpose of bi. Yi be a transpose of bi. And constraint write in A transpose of y. If a problem is less than equal to, we write greater than equal to, obviously. And here we write as C, cost transpose. Write the cost transpose. So we remember all these points before we writing the dual of any programming problem. So we take first problem. That means this problem we write as minimize of z. Minimize of z equal to. This can be written as 10x1 plus 15x2. So this is the cost. 10 and 15 we write in the matrix form. That means this is the matrix of 1 by 2 order, and x1 and x2. 10x1 plus 15x2, and subject to constraint. For writing subject to constraint, we write also in this form in the matrix, that means 5, 7, 6, 11. 5, 7, 6, 11, x1 and x2 less than equal to v. V means 80 or 100. Sorry, here is the greater than equal to. This is the greater than equal to 80 and 100. So we see that means this matrix we denoted as A. This is denoted as X, and this is denoted as B. So AX equal to B, that means greater than equal to B or less than equal to B. And all the decision variables we write as x1, x2 greater than equal to 0. So now the dual of above problem. We convert minimization into maximization. First we write is maximization. Maximize z. So write z. Here we use the variable x, so we write as zx. We use the variable y, so we write as zy. So this equal to we write here b y b y1 into v1 transpose. So B1 transpose into Y. So B1 is 80, 100. So we take its transpose. We take its transpose, so that is 80 and 100, and write as Y1 and Y2. So B transpose. And a subject to constraints, we take the transpose of A. When we take transpose of A, so we write this transpose as 5 row into column, column into row, so 6 into 11. And we take other variables such as Y1 and Y2. And reduce the problem with less than equal to and write as C. C dash, C. The transpose C. C means this is C, 10 or 15. So we write as 10 and 50. 10 and 50. So again we write all the decision variables also greater than equal to 0. So this problem can be written as maximum of Z into Y, 80 Y1 plus 100 Y2, and subject to constraints 5 Y1 plus 6 Y2 less than equal to 10, 7 Y1 plus 11 Y2 less than equal to 15, and Y1 Y2 which is greater than equal to 0. So such type of problem is known as the dual of the given problem. So first we formulate the problem. After formulation of the problem, we write the dual of its problem. So while we solve the problems, that means in primal form, this is the original form, or in the dual form, solutions remains same. And we already discussed that means when we solve direct primal problems, maybe take times and it is difficult to solve, rather than we solve by using the its dual problem. Dual problem is quite easy to solve. So here we see that this problem having less than equal to sign, so we use simple simplex method or we use the graphical method. While we use the simple simplex and have a problem having greater than equal to sign, we use the Begum and Duplex method. So in place of simple simplex or Begum, so we can say that the simple simplex is quite easy to use to solve the problems. So the associated LPP is considered as the dual of given primal. Considered as a given primal form. Okay. So first we formulate this problem, and after formulating we write the dual of this problem. So before writing the dual of this problem, that means we familiar with the terminology. These terminology means these steps. So the given problem known as the primal form having objective function is less than equal to, that means minimization, and dual which is maximization. And if problem less than equal to, we write the dual of which problem is greater than, or vice versa. Next, while the problem has equality constraints. Equality constraints. For example, that means problem having such type of constraints x1 plus 2x2 equal to 4. So what to do for solving that, we writing the dual of this problem. So first we make this problem into less than equal to or greater than equal to form. So is the equal to sign replace into two inequalities, into the two inequalities. One is less than and other one is greater than. So less than and greater than. So that means we write this form as x1 plus 2x2 less than equal to 4, and another one we write as x1 plus 2x2 greater than equal to 4. While we solving the problem, that means every constant having same sign, so then we multiply by -1. That means if a primal form having all constants having less than equal to sign, but one constant having greater than sign, so we make less than equal to sign by using multiplying by -1. Remember this? So by multiply by -1, and so any equality problem converted into the two inequalities. One is less than equality, or second is greater than equal. So when we want to make this problem as a less than equal to problems, just we multiply -1 minus 1. So you can write this form.